photoelectric effect. The photoelectric effect was a very important discovery that was made in the early 1900s and was first correctly interpreted by Albert Einstein. The photoelectric effect shows us that when light strikes a metal surface, electrons are ejected from that metal surface. The first important thing you need to know is that the brighter the light, the greater the current. That is, the greater the number of electrons that are ejected from the metal. So a brighter light creates a larger current, which means more electrons ejected from the metal. You'll notice it's a linear relationship that goes through zero. So no matter how low the intensity is, as long as you're not at zero, you'll still have some electrons being ejected from the metal. Okay, the second thing that you need to know is that these electrons that are ejected from the metal have a certain amount of energy. That energy was determined by using a voltage source to try and stop the electrons. So we make one of these plates negative, and it starts repelling the electrons away from it. And when we hit just the right voltage, we'll get it so that none of these electrons can make it across to the other plate. At that point, the current will drop down to zero. Once we have the current down at zero, we can find the energy of these electrons by using the formula. Voltage, that's the voltage of our voltage source, is equal to the kinetic energy of the electrons, which will go from the formula voltage equals work over charge. Again, the work is the kinetic energy of the electrons, the Q is the charge of the electron, and V is the voltage required to stop the electrons. We know we stop the electrons when the current gets down to zero. Okay, so we now know that brighter light knocks off more electrons. We now know the energy of the electrons, and we know that energy is determined by the voltage required to stop them. We now want to see, is there any relationship between the energy of electrons and the light that we're shining onto the surface. So if you notice this graph, as we increase the frequency of the light by decreasing the wavelength, you'll notice that the energy of electrons increases. Similarly, when we lower the frequency of the light, the energy of the electron decreases until eventually you hit a point where no more electrons are ejected from the metal. At that point, you have been said to cross the threshold frequency or the threshold wavelength for that material. From that point on, no more electrons will be ejected from the metal. Each type of metal will have its own threshold. So the first metal we did was calcium. We're now going to look at it for sodium. And you'll notice that it has a lower threshold frequency. It's easier to knock the electrons off of sodium than it was calcium. And then when we switch over to a metal like copper, and we examine copper, we'll see that it has a much higher threshold frequency. Regardless of what type of metal we use, it turned out that the slope of this graph was always the same. So if you took the slope of this graph, no matter what metal you used, it turned out that the slope was equal to some number, and that number is now known as Planck's constant. It goes by the letter H. When we write the equation for this graph, y equals mx plus b, you'll notice kinetic energy of the electron is on the y. The slope of the graph was equal to Planck's constant. So y equals m. In place of m goes Planck's constant. Frequency is on the x-axis, so that takes place of the x. And then minus the y-intercept. And it's minus because the y-intercept is below the x-axis. And it turns out that y-intercept is determined by the type of metal that you use. And it goes by the letter standing for the work function of that metal. Each metal has its own work function, and that will help you determine how much kinetic energy the electrons are going to have. The importance of this experiment showed us that when light is shined on the metal, that light comes in small bundles known as photons. And when those photons hit the metal, if that photon, whose energy is hf, is greater than the work function of the metal, then an electron will be ejected from that metal surface. If the photon has less energy than the work function, then the electron will not be ejected from the metal. This showed us for the first time that light comes in discrete packets of energy, and those little packets of energy are known as photons.